All right, everybody, we're going to be working on our second standard here, and that is going to be to write and interpret models of rational functions and variation. And this time we're going to simply work with writing rational functions. So we're going to be writing the f of x equals and using all the information that we know about our functions to create the equation that fits that information. Let's take a look. All right, I've got three examples. The first two are going to be given some information, and the last example is going to be given a graph where we have to extract the same type of information. So I have here that I have two x-intercepts, and I have a vertical asymptote at -2 and a horizontal asymptote at +2. So that information is going to lead me to writing my equation. And we'll start off always with f of x equals, and it's going to be a fraction because we're working with rational expression or rational functions. My x-intercepts, they came from the numerator when the numerator equaled 0. Oops, num equaled 0. So my numerator had to equal 0. My vertical asymptote, that was where the function was undefined. So that must have been when the denominator equals 0. And my horizontal asymptote being y equals 2, because it's y equals 2, that must be the ratio of the lead coefficients of the numerator and denominator. So that's what that information is. So to put this back into a function, if my x-intercepts are where the numerator equals 0, that meant that x plus 4 and x minus 2 were the information from the x-intercepts. My vertical asymptote x equals -2 is where the denominator equals 0, so that must be where it was undefined. So x plus 2 was where it was undefined. Now, having a ratio of lead coefficients also means that I had the same degree. And if you notice right now, I have going to have an x squared in the numerator from having x times x, but I only have an x in the bottom, which means that I don't have the same degree. So we have to fix that by not adding any extra information, but just by squaring the denominator. So that doesn't create a new place. Okay, it just, it re-emphasizes that. So it gives me the same degree, and that's what I needed to have, was the same degree. So I can change it by just squaring the denominator. And then lastly, I have to go back to that ratio of lead coefficients and make it 2 over 1, because that's a 2 over 1. And I can do that simply by putting out just a 2 in the numerator. So when you were to multiply this out, which you do not have to do, I would get a 2x squared, and in the denominator I would have a 1x squared. So I get the ratio of 2 over 1. Let's do the same thing with the next one. For here, this is for my x-intercepts, that's when the numerator equals 0, because that's what makes a fraction equal 0. My y-intercept, not having a y-intercept, now this information is going to lead into the next piece. When I have a vertical asymptote at x equals 0 and at x equals -4, that's when the denominator was equal to 0 because it gave me an undefined function. And then my horizontal asymptote being y equals 0 means that it must be bottom heavy. Okay, all right, so let's go ahead and take a look at what that gives us. So I'm going to start with f of x equals a fraction, and my numerator equaling 0 would give me x plus 1 and x minus 5. All right, with the vertical asymptote at x equals 0, that means that I have an x and I have an x plus 4. So right now I have the same degree, and right now, if you were to multiply these out, you would get x squared minus 4x minus 5 over x squared plus 4x. And what happens then is if I were to, then I'm going to go back to my y-intercept. If you were to substitute in 0, you would get a -5 over 0, which means I would not have a y-intercept. So this actually proves to me that I do not have a y-intercept. By substituting in 0 for x, I can check to see that I'm not going to get a y-intercept. Now, being bottom heavy means that I had to have a bigger degree on the denominator. So one thing has to happen. I have to change the exponent exponent on one of these guys. We have to make one of those squared so that I have a larger degree on the denominator, which gives me the bottom heavy idea. So I'm just going to go ahead and make this one squared. It doesn't matter, you can make just one of them squared. So then that is my final answer. All right, now using a graph, I'm going to try to pull out the same types of information. And that is, I'm going to pull out, let's see, I can see that I have a vertical asymptote at x equals 2. I have a horizontal asymptote at y equals 1. And I have an x-intercept at 1, 0. Now, I can see that I do have a y-intercept, but it's not really clear, and I don't want to guess and just go, well, it looks like 1/2. I'm not going to guess, so don't guess on that. Okay, so using the information from the vertical asymptote, that tells me when the numerator was equal to 0. So I have f of x equals, and my numerator would be x minus 2. A horizontal asymptote of y equals 1 tells me that my lead coefficient ratio is 1/1, but I also have to have the same degree, so keep that in mind. My x-intercepts, oh my gosh, Miss Moran, this should be the denominator equals 0. I hope you caught me. And then this one tells me that my numerator must be x minus 1. All right. So let's just double check to see that we've used everything. So I have my vertical asymptote in the denominator because that's where it's undefined. Okay, I have a horizontal asymptote with a ratio of 1:1, but I have to have the same degree, and I do. I have an x-intercept and the numerator, so that's when the numerator equals 0, and that gives me my x minus 1. You don't need the ones out front. My y-intercept happens to, looks like it's going to be 1/2 when you put in 0, so you get the 1/2, so that looks approximately right. At least it wasn't bigger. And this will be our function, which I'm going to rewrite because I got sloppy. X minus 1 over x minus 2. All right, great job.